So we looked at the simplest calculation where we took the energy coming in from the sun intercepted by the surface area or the area that is projected by the earth spinning around. We have ignored the tilt and so on. And we just equated the net energy coming in to the net energy going out. There was no greenhouse effect because we didn't put any atmosphere. So in that case, the energy is balanced basically from the outgoing long wave, which gave us a temperature of 255 Kelvin, which is the the emission temperature at the top of the atmosphere. But if you put the atmosphere, then the key question is what happens to the surface temperature? The surface temperature is not emitting directly to space all of the energy. It's going through the atmosphere. So then the internal bouncing around of the energy has to be understood. So we start that with a simple greenhouse model where we add a layer of the atmosphere which can absorb the energy now that is coming from the surface as well. Okay? And for simplicity, we'll assume that the atmosphere is completely transparent to the incoming shortwave energy, which is not true, as we already know, and goes directly to the surface, and that energy is going to warm the surface and send outgoing long wave. But once you have the atmosphere, you obviously also get energy coming down from the atmosphere. So here it is. Energy coming from the sun here is why is it divided by 1/4? We already saw that. Oops, where am I going with this? We had already done this, so let's do it again. Okay, so before we did the balance on the whole globe, so we just took the energy coming at the top of the atmosphere, the energy intercepted, and equated them. But when you want to do these greenhouse calculations, you have to now go down to a square meter of the earth and look at energy coming in and energy going out, energy coming in from the sun and from the atmosphere, and energy going out from the surface and from the atmosphere. So a little bit more complicated, but it's still very simple arithmetic. So we now go down to the square meter, which means the energy that was being intercepted by the earth has to be distributed on the sphere. Remember, during the day or the earth is spinning, so the sun's energy is being received by every square meter of the earth that is seeing the sun, and that every square meter is related to the surface area of the sphere, right? So that we will see in a minute. So S0 divided by 4 is what is coming in, but albedo alpha bounces back, reflects alpha times S0 over 4 straight back, and since the atmosphere is transparent, we are going to be retaining S0 over 4 minus alpha S0 over 4 as the net short wave that is given to the system. But now the energy that is going from the surface is going to be intercepted by the atmosphere. So the atmosphere, which is a greenhouse atmosphere, we are going to assume is completely opaque to the outgoing long wave or thermal energy or the heat energy coming from the surface. So it's going to absorb all of this S or the thermal energy coming from the surface, and it's going to keep it and warm up to a temperature TA. And that temperature TA is actually a net of what it will send to space, but also downward, because any black body is going to emit radiation in every direction. So if you have the atmosphere above the surface, atmosphere is going to send energy to the to space as well as back down. So the net temperature TA is determined by the energy received from the surface, and then it's going to be bounced up and down. Okay, so how do we do the energy balance? We just look at the net energy coming in, which has to determine the net energy that is received by the atmosphere. So let's look at the intercepted incoming radiation, which was S0 over pi a squared, and we have to divide it by the surface area, because now we have to look at each square meter instead of averaging over the whole area and balancing. So we are going to divide it by the surface areas. That's how we ended up with each square meter receiving S0 divided by 4. S0 is the solar flux received at the top of the atmosphere, but we know that alpha times S04 is bounce back, and the atmospheric thermal energy or heat energy is of course again given by Stefan-Boltzmann law, which is sigma Ta to the fourth. What do? We are going to balance the energy that the atmosphere is emitting to the energy that is received by the system. Why? Because in this case, the simple case we have created, the incoming solar energy is what determines net emission temperature, or the sigma Ta to the fourth. Whatever bouncing around happens, it doesn't matter. What goes out has to equate the energy that is coming in. It's really that simple. Okay, so sigma Ta to the fourth is also equal to sigma Te to the fourth, because now the atmospheric layer itself is emitting to space, and that's the effective emission temperature. So it's just a little nomenclature thing. We can call it atmospheric temperature because that's what it is. We can also call it emission temperature because that's what it is. But that is determined by how much energy, shortwave energy, is being retained by the system, which is 1/4 times 1 minus alpha p, the planetary albedo, times S0, which is the solar flux at the top of the atmosphere. Very, very, very simple. What else do? We now take this downwelling. So here we looked at upwelling long wave radiation from the surface to space, which is what we balanced here. But now we also have that energy going down to the surface, which is still the same. Sigma Ta to the fourth is going up and down because black body emits in all direction, and that is still sigma Te to the fourth. But at the surface we have energy coming up into the atmosphere as long wave or thermal or heat energy, which is sigma Ts to the fourth, where Ts is the surface temperature. Okay, because the surface is warming, it is also emitting thermal energy or heat. And now we balance the net thermal energy of the surface to the shortwave energy it is receiving plus the heat energy it is receiving from the greenhouse atmosphere. Okay, very simple. Go back to the figure and see the energy. Let me go back. This energy has to equal the net shortwave coming in plus the long wave or the heat coming from the atmosphere. That's all. So just listen to it, go through it, make sure you understood it. Okay, so sigma Ts to the fourth, or the outgoing long wave from the surface, has to equal the total energy received by the surface, which is short wave plus the long wave from the surface. So then sigma Ts to the fourth, which is the thermal energy, has to equal this, where A is again Te, sigma Te to the fourth. So this is already sigma Te to the fourth by balancing the energy at the top. So the net energy was 1/4 1 minus alpha T alpha P as 0, and the outgoing was A going out. So that's what we had written before here, right? So plug that in and you end up with sigma Ts to the fourth equal to 2 times sigma Te to the fourth. So that gives us the surface temperature, which is 2 to the 1/4 Te. This is a critical result because this says if there is a greenhouse layer, then the surface temperature warms compared to the emission temperature. When we had no layer, the surface temperature was the emission temperature of 255 Kelvin, which is too cold, we know that. But when we add a simple greenhouse gas layer, we end up with surface temperature that is 2 to the 1/4 Te. Te has to still remain 255 because we are still balancing energy at the top of the atmosphere. So now you multiply 255 by 2 to the 1/4, you end up with 303 Kelvin as the surface temperature, which is obviously too warm. We know that it is 288 Kelvin. So why did this happen? Obviously because we simplified the greenhouse layer into one layer, and we made it transparent to shortwave, and we made it completely opaque to the energy coming up from the surface. This is not the real situation. So in the real world, you want to add more realism. So then in that case, the atmosphere is, for example, not completely opaque to the energy coming from the surface. It will have an emissivity, so it's called a leaky greenhouse. So instead of keeping all of the surface energy coming up, it will keep part of it related to its emissivity, and it will allow some of it to escape. So 1 minus epsilon times S is what gets transmitted through the atmosphere, and the atmosphere still has a temperature TA here, so it is still going to emit heat energy up and down, but now this TA will be different than when we didn't allow the atmosphere to keep sorry when we didn't allow the any of the heat energy from the surface to escape through the atmosphere. Okay, very simple modification. So in that case, we can still balance the net energy received in the system to the outgoing long wave from the atmosphere and what is escaping from the surface through the atmosphere. Okay, so it will be A going up plus 1 minus epsilon times S. S is here. This is solar radiation flux received at the top of the atmosphere. This is heat energy coming from the surface. So make sure you understand the symbol. So here it just gets a little bit more complicated. And again, we can write the balance for the surface. Surface is receiving the short wave plus energy from the atmosphere, so that has to equal its outgoing long wave, and that gives us a little bit more complicated expression for the surface temperature. Surface temperature now looks like this. So it looks like 2 divided by 2 minus epsilon to the 1/4 times TE. When atmosphere is completely opaque, obviously this becomes 1. So then you still get 2 to the 1/4 TE as we did before. But if epsilon is less than 1, in which case the atmosphere is leaky, so it will only keep part of the energy coming from the surface, then this will change the surface temperature. Very, very simple. Okay, so in general, epsilon varies from 0 to 1. 0 is when it's completely opaque, and 1 is when it's completely transparent. 0 is when it's completely transparent, and 1 is when it's completely opaque. So in that case, the emission temperature will be less than Ts, and that will be less than 2 to the 1/4 T. So this is the maximum surface temperature you can get when the atmosphere absorbs all of the heat energy coming from the surface. If it allows some of it to escape, the atmosphere will cool because it's losing some of the thermal energy from the surface, and that means the energy received by the surface also decreases, and the surface will also get cooler than 2 to the 1/4 times TE. Very, very simple. We can of course do this in some detail. So energy going up and down from the atmosphere is the same, so that is epsilon times sigma TA to the 4th, because atmosphere has an emissivity or transmissivity. So then you can relate the net solar energy to energy coming from the sun plus the energy coming from the surface, and we already I'm repeating this for some reason. Okay, so that's the relation. This is the coolest temperature you can get when you have epsilon equal to 0 and the atmosphere is completely transparent, in which case the atmospheric temperature will be related to surface temperature this way, which of course is what we saw before. Ts is 2 times 1/4 to TE. Okay, so to add more complexity, basically we can keep adding more layers, layer A and B, then you bounce energy between them, or you can add n layers and you can continue this simple calculation, linear algebra, linear arithmetic calculations, and show that surface temperature becomes n plus 1 to the 1/4 times T1, where T1 is the top of the atmospheric layer, top nth layer, and that will have 255 Kelvin, because this still has to be the outgoing emission temperature, because you are just balancing incoming solar to outgoing long wave at the top of the atmosphere. So the main story is that greenhouse layers basically bounce around the energy from the sun and they warm the surface. This is what greenhouse effect and global warming are all about. As we increase greenhouse gases, we are trapping, we are creating greenhouse layers, and we are keeping more of the energy, and we are warming the surface, and we are melting glaciers, we are evaporating the oceans, and so on, and creating all sorts of feedbacks, which is what we are mostly worried about under global warming. Okay, so this is a little bit long, but it's worth listening to, because we had to go through these tiny steps, and make sure you can sit down and work it out, because it looks very simple. You can listen to it as many times as you want to make sure you understand how the energy is being bounced around. So starting with no greenhouse, adding one layer, and then thinking about how to add another layer or n layers, you can easily derive these relations by yourself. Okay.